All right, this video, we're finishing the related rates notes. We're going to start with example 3. A conical water tank with vertex down has a radius of 10 feet at the top and is 24 feet high. So I'm going to go ahead and put those measurements on my diagram. 10 feet at the top, 24 feet high. If the water flows out of the tank at a rate of 20 cubic feet per minute, that is our change in volume over our change in time. And so I already know that this is a volume problem. How fast is the depth of the water decreasing? So I'm looking for the change in the height over a change in time. That's my question mark. And we're looking for that change in height at a height of 16. So if I look at this little diagram right here, as the water is flowing out, the change in the radius and the height are both variables. They're both changing here. And so if I write down my formula for volume, volume is 1/3 pi r squared h. Now you are going to need to memorize most of your formulas like Pythagorean theorem, area of a circle, but for volume of a cone or a sphere, that should be given to you. But it's good to know those anyway. All right, so if I use implicit differentiation, differentiate both sides of this equation, I'll have dv dt, and that's given. 1/3 pi, those are just numbers. I am going to have r and h. I'll have two variables. And so we can only solve when we have one variable, so we need to use similar triangles to relate the radius in terms of the height. Okay, so see, we've got these two similar triangles, and we have an r and an h. And so I can set up a ratio. R over 10 is equal to h over 24. And then solving for r is equal to 10h over 24, or 5h over 12. All right, so now I'm going to make a substitution for the r in my formula. And so I'm going to have volume is, and I'll just clean this up, pi over 3. And then r is now going to be 5h over 12 squared times h. All right, so one more quick cleanup here. Pi over 3, this will give me times 25 h cubed over 144. If I distribute the squared, and then this is going to be h squared times h, that makes h cubed. So now when I differentiate, dv dt is equal to, if I use the power rule, the 3 is going to come up front and will cancel with the 3 that's in the denominator here. So this will give me just pi times 25 over 144 h squared dh dt. All right, so let's substitute in. We know that dv dt is 20, and this is 25 pi over 144, and we're looking at a height of 16, and times dh dt. All right, so let's just make sure I made all these substitutions. dv dt was given at 20 cubic feet per minute. I just kind of cleaned up all of this. 25 pi over 144 at a height of 16, that was given, squared, and then the rate of change, of course, the chain rule, dh dt, and that's what we're solving for. So now let's go ahead and divide both sides by all of this and isolate our dh dt. So dh dt is going to equal to 20, and let's see if I can just do a quick little, let's see, 256, this is 256. So that's 256 times 25, and let's see, what is that? A little calculator real quick, 256 times 25, 6,400. So this is 6,400 pi, and if I multiply by the reciprocal, so this is going to be times 144 over 6,400 pi. And let's see, I can cancel a 0. So 2 times 144 is 288 over 640 pi. And I think that, let's see, 288 divided by 640 is 0.45 pi, or And 0.45, what is that? 9 over 20, so 9 over 20 pi. There it is. dH dt equals, and that is feet per minute. That is the change in the height over change in time at the instant that the height is 16 feet. Okay, let's try another example. This time we have a table, and it tells you that the volume of a spherical hot balloon expands as the air inside is heated. The radius of the balloon is modeled by a twice differentiable function, r of time t, where t is measured in minutes. The table gives selected values of the rate of change in r of the radius over the time from 0 to 12. The radius of the balloon is 30, so r is 30, the time is 5, and here's our volume. It says find the rate of change of the volume, so that's dV dt, that's what we're looking for, with respect to time when time is 5. Okay, so I'm just going to differentiate this volume formula, and let's see, if I use the power rule, 3 will come up front, the 3 will cancel with the 3 in the denominator, and so that's just going to give me 4 pi r squared dr dt. All right, and let's substitute in some values. So dV dt, that's what we're solving for, is equal to 4 pi at a radius of 30, and the rate of change at a time of 5, if we go to our table, the rate of change is 2. So I can substitute in dr dt is times 2. All right, so 8 times 30 squared, well, let's see, I'm trying to do too much in my head, times 900, and that's going to be 7200 pi, and that is in feet, cubic feet, because we're finding the rate of change of volume per minute. All right, the next one I'd like for you to try on your own. Pause the video and then come back and let's work it. All right, so hopefully you did that, and we can just check your work. So the radius of a circle is increasing at a constant rate of 2 meters per second. So the first thing you should have written down is dr dt. The change in the radius over the change in time is 0.2 meters per second. What is the rate of increase in the area? Okay, so we're looking for dA dt, the change in the area over the change in time. An area of a circle is pi r squared. It says the instant when the circumference is 20. So we're given that the circumference is 20 pi. Well, I need the radius, but I do know that the circumference is 2 pi r. So I know that my radius is going to be 10. Okay, so now dA dt is equal to, well, if I differentiate this will be 2 pi r dr dt. And then if I make a substitution for r and dr dt, dA dt is equal to 2 pi times 10, and dr dt was given at 0.2. So 2 times 0.2 is 0.4 times 10 is 4. So the change in the area over the change in time is 4 pi meters squared per second. This last example, excuse me, we have got a camera mounted 3,000 feet from the Space Shuttle launch. So this distance here is 3,000. Here's my camera, and it is capturing the Space Shuttle as it rises. And so here is my right triangle. And as the Space Shuttle increases, this distance from the camera to the Space Shuttle increases. So the camera needs to pivot as the shuttle's launched and needs to keep the shuttle in focus. If the shuttle is rising vertically, okay, so here's my first piece of information. And I'm going to call this Y, and I'm going to call this guy X. And this is a right triangle, so I'm going to call the distance from the camera to the shuttle Z. And so already in your brain you're thinking, oh, this is a right triangle, Pythagorean theorem. And that's exactly what we're going to use. But I'm given some information. this is rising. dy dt, the change in the height, is 800 feet per second when it is 4,000 feet high. So at a y value of 4,000. So this is looking nice because this is a 3, 4, 5 triangle. This is one of our Pythagorean triples. So we know some values here. So how fast is the camera to shuttle distance changing? So remember, the camera to the shuttle is z. So we're looking for dz dt. This is our question mark. All right, so to relate these three quantities together, that is Pythagorean theorem, x squared plus y squared is equal to z squared. If I differentiate this, this is going to be 2x dx dt plus 2y dy dt is equal to 2z dz dt. Divide everything through by a 2 just to get rid of that. I'm going to have x times dx dt plus y dy dt is equal to z dz dt. Okay, so x is the distance from the camera to the launch pad. That's 3,000. This does not change. So the rate of change in x over time is 0. So this is going to be 3,000 times 0. So that's just 0. Okay? So then we have plus y is 4,000. The rate of change of y is 800 feet per second. And the z is 5,000, and we're trying to find dz dt, the rate of change in the distance from the camera to the shuttle. So we have 3,200 is equal to 5,000 dz dt. And if I just divide both sides by 5,000, let's see, 32 over 50 dz. Uh-oh, did I mess up? Let me double check my work here real quick. That is not looking right. I'm going to go ahead and let's see. I'm going to back up, make sure I didn't make any mistakes. So this is 3,000 times 0 plus the y value times the change in y is equal to the z value times the change in z. And we're trying to find the change in z. So that's, whoa, I think I don't have enough zeros here. Back up, just 1 second. So this is 4,000 times 800. That's 32 with 1, 2, 3, 4, 5 zeros. I clearly did not have enough zeros. Is equal to 5,000 dz dt. All right, back on track. Now let's divide by 5,000. So 32 with 5 zeros divided by 5 with 3 zeros. 1, 2, 3. 3,200 divided by 5. That's more like it. How about 640? And this is feet per second, is the change in the distance over time. Okay. One last problem to look at, and this is just a problem from the 2002 AP test, and we'll look at the scoring guidelines. It is a right triangle problem, so we're probably going to be looking for Pythagorean theorem. So ship A is traveling due west toward Lighthouse Rock. So right over here, we've got ship A coming this direction here. Ship B is traveling due north from Lighthouse Rock, and we're given their rate of change. Let x be the distance between ship A and Lighthouse Rock, and let y be the distance between ship B and Lighthouse Rock. Find the distance between ship A and ship B when you've got x is 3 and y is 4. So this guy is 4, this guy is 3. We know the distance here, but Pythagorean theorem is going to be 5 kilometers. Now we find the rate of change of the distance between the two ships at this time. And so we would differentiate our Pythagorean theorem and then sub in the values that we know. I'll show you the answer key on the next page. And then the last one is let theta be the angle shown in the figure, and find the rate of change of theta in radians per hour when x is 4 and y is 3. And that's very similar to the problem that we worked in the day 1 notes. So here's how they scored it. You're going to get your 1 point just for your Pythagorean theorem. And then here is the Pythagorean theorem, and if we implicit differentiate it, you need to show this. And then we make some substitutions in at a time of 4 and 3 and the rate of change of those. We're going to get -6 kilometers per hour. All right, and so you get 1 point for the expression, 2 points for differentiating with respect to t, using the chain rule, and then 1 point for the evaluation. And then here's the third part, the change in theta over time. So again, using tangent, and if we differentiate that, derivative would be secant squared, and then we have the quotient rule. Sub in the values that you know, and then secant 5/4, and clean it all up, we get 17/5 radians per hour. So this is worth 4 points. So you get 1 point for just writing this guy, 2 points for differentiating and using the chain and the quotient rule, and then you have 1 point for your answer. All right, it is definitely time to practice.